Ele precisa contar. Um, dois, três, quatro, cinco. Você subiu lá.
Okay, good afternoon, everybody. We are happy here to have this colloquium in person. So, and also for me, it's a big pleasure to introduce Dr. Gøran Nilsen from ICE's Neutron and Muon facility in Rutherford Appleton Laboratory. So the reason that Dr. Nilsen is visiting our institute, he's actually a visitor researcher FAPESP fellow, and he's in between the activities actually was to extend collaboration with researchers in Sao Paulo, and also he gave a mini course to our postgraduate program about diffraction neutron scattering. And before start your talk, I wanted just to introduce briefly a bio about you. Dr. Nilsen did his undergraduate in chemistry at University of Edinburgh. After he moved to École Polytechnique Fédérale de Lausanne, where he obtained his PhD in chemistry and physics in 2010. Between 2010 and 2015, he was working in several postdoc and scientist instruments in institutes like University of Bern, University of Tokyo, and the Lowy Langevan Institute. Okay, and since 2015, actually, he's a permanent scientist instrument in the ICE's Neutron and Muon facility in United Kingdom. And his main activity is use the polarized neutron scattering to study hot topics in condensed matter physics. And this is one actually of your subject. And for us, we are glad to listen to your talk about recent achievement in polarized neutron scattering. So please, whenever you want, start.
Well, let me switch on. Right, is that working? Can everyone hear me? And online as well, hopefully. Right, well, I can't see anyone's webcam, so I'll just assume it's okay for the moment. So first of all, thank you. Oh, right, that's good news. So thank you very much, Professor Julio, for the very kind introduction, and also for inviting me to come here and hosting my visit here. And thank you also very much to Professor Valentina Martelli, who's also in the audience today, for hosting me. So I've been in Sao Paulo for about 3.5 weeks now, and I've really loved it. Unfortunately, there's only a couple of days left until I go home, but I plan to make the best of them. And with that, I'll start my talk. So today I'll be talking to you about dynamics in condensed matter, and specifically how we can access this dynamics using polarized neutron time-of-flight spectroscopy. So I'll be focusing mainly on systems ranging from soft matter to biological matter, and then I'll talk a little bit about hard condensed matter as well, because this is really a universal technique that can be applied to almost any condensed matter system. Right, so before I begin the scientific part of the talk, I'll tell you a little bit about where I work. So I work at the ICE's Neutron and Muon facility, which is part of the Rutherford Appleton Laboratory, which is about 100 kilometers outside of London to the west. So here's a picture of the Rutherford Appleton Laboratory. It's near a little town called Didcot and a village called Harwell. And it features not only the ICE's Neutron and Muon facility that you can see here in the foreground, but also the UK's National Synchrotron facility, the Diamond Light Source, and the Central Laser facility, as well as many different companies and other organizations on site. So the whole site, called the Harwell site, employs about 7,000 people, of which about 2,000 work at the Rutherford Appleton lab. And as you can see, it's kind of in the middle of the nowhere in the countryside. It's about 25 kilometers from the city of Oxford. And as I mentioned at the start, it's about 100 kilometers or a 45-minute train ride away from London. So let's have a closer look at the ICIS facility. So here's a bird's eye view of the facility, which consists of an accelerator, which is in 3 stages. There's a LINAC, a synchrotron, and then an extracted proton beam stage. And these lead to 2 target stations. So I'll just quickly show you how this accelerator works. So the beam starts with negative hydrogen ions that are accelerated in the LINAC. The electrons are then stripped away, and the neutrons are sent into the synchrotron. That happened a little bit too quickly to see, but we'll hopefully have a repetition now. Yeah, so it's sent out to the synchrotron where it's accelerated to about 84% the speed of light, and then it's impacted on a target, one of 2 targets, which are made of heavy metal. It's tungsten tantalum targets, and these emit through the process of spallation neutrons that we use for our condensed matter research. Right, so we, as I said, have 2 target stations at ICIS. There's this original one from 1985, and then there's this more recent one from about 2007. And the one from 1985 specializes in experiments that use warmer neutrons. I'll explain what that means in a moment, whereas the one on the newer one specializes in cold neutrons. So the layout of each target station is like this. So the beam comes from this direction and hits the target, which is inside this cylinder, where the neutrons are produced. Then they're thermalized and transported out to instruments that are arranged radially around the target. And these instruments cover a huge range in time and in space, so that you can investigate phenomena all the way from angstrom up to micrometers, and from picoseconds to nanoseconds. And these 34 instruments that we have at ICIS, of which 29 are neutron instruments, by the way, we have 3,500 roughly annual user visits. Of course, this was pre-pandemic. We haven't had so many in the last couple of years. These are supported by about 500 staff and produce annually in the region of 650 journal articles. And as I mentioned, this is a very versatile source. There's instruments for everything there, and that's reflected in these publications. So these total 640 odd publications, we have a nice distribution across areas going all the way from materials science, physics and astronomy, chemistry, chemical engineering, all the way to architectural heritage. So in recent years, people have even attempted using neutrons to look at ancient weapons, for instance. And with that small promotional part for ICIS out of the way, I'll now start on the scientific part of the talk. I'll begin by discussing neutron scattering, so what it is and how it works, and then how polarization analysis can be used to enhance the information that you get from a neutron scattering experiment. In the second part of the talk, I'll talk about polarization analysis on a particular instrument at ICIS, the LET time of flight spectrometer. And here I'll go through the instrument concept and just very quickly the technical implementation, because I can't imagine that that interests you too much. And then I'll finish with a range of case studies, which, as I said at the start, go all the way from liquids to soft matter in biology to hard condensed matter. So firstly, why do we use neutrons in scattering experiments? Going back to 1932, Sir James Chadwick discovered the neutron, and it was quickly found that the neutron not only has zero charge, but it has a similar mass to the proton. And crucially, it has a magnetic moment related to its spin of 1/2. And all of these properties are extremely important to why neutrons are used so widely today. So the neutron as a subatomic particle obeys the laws of quantum mechanics. So in other words, a wave-particle duality. So although we conventionally consider it as a particle moving with some velocity associated with a kinetic energy and momentum, we can equally consider it in some situations as a plane wave through the famous de Broglie relation. This plane wave has a wavelength related to the momentum k, which is just the momentum over h bar. So depending on the situation in neutron scattering experiments, we alternate between these descriptions of the neutron, although perhaps the most correct one and one that we rarely have to use is that of a wave packet. So there are two ways to produce neutrons, conventionally at least. One I've described just now, it's spallation, where you use a proton accelerator and a heavy metal target to induce spallation, which produces a large number of neutrons per proton heavy metal collision. So you come in with a high energy beam, about 1 gigaelectron volt, and collide it with this target, and each of these collisions generates about 30 or 40 neutrons. The other way, the more conventional, old-fashioned way, is to do it by nuclear fission of uranium. And this generates both lighter elements and many excess neutrons per fission. But regardless of how you generate your neutrons, in order to make them actually useful, they need to be moderated. So typically the fission and spallation neutrons are emitted at energies of mega electron volts. And then to bring them down to an energy range and conversely a wavelength range where they can be used for scattering experiments, they're moderated in some kind of material. So this can be, for instance, water at room temperature. It can be hydrogen at 25 Kelvin. It all depends on the spectrum that you want of neutrons. And the way this works is basically that the neutron comes in and it thermalizes via collisions in this medium, in the moderator. So the typical neutrons that we get from different moderators range usually from about 1 to 1,000 millielectron volts. So many, many orders of magnitude smaller than the ones we get from fission or spallation. And at those energies, again, using the de Broglie relationship, in the wave picture of the neutron, you have wavelengths ranging from about 0.3 to 9 angstrom. So these are wavelengths that are compatible with atomic spacings and materials, and therefore we can learn about atomic structure using neutron scattering. And fortuitously also, these energies are compatible with typical processes, dynamic processes in materials. And this is what we're going to be using later on to investigate the dynamics of materials. So in neutron scattering, the typical experimental setup looks something like this. You have some incoming beam, which you consider as a plane wave characterized by some incident wave vector ki. It hits a sample shown in green here, and then it's scattered into some solid angle with a final wave vector kf. Now, in that scattering process, there is a transfer of momentum to the sample, described by this scattering vector q, which is ki minus kf. And there can also, in the case of inelastic neutron scattering, be a transfer of energy into the sample as well. And the neutron, unlike the X-ray, doesn't interact with the electrons on atoms, but rather with the nucleus itself through the strong nuclear force, which is a very short-ranged force. It has a range of about 1 femtometer. And this has a number of important consequences. So firstly, diffraction using neutrons is very similar to diffraction using X-rays. So here's an example on the left of a diffraction pattern from an organic compound called benzyl, which is this molecule shown here on the right. And a key difference due to the interaction of the neutron with the nucleus rather than with the electron cloud is that you don't have a form factor. You'll see that the intensity in this diffraction pattern, even as you go very, very far out from the center, remains fairly similar. Whereas in X-ray scattering, it would drop fairly rapidly. And this also means that you're able to measure things like thermal displacement factors, atomic position parameters with greater precision than using X-rays. Another advantage of neutrons in this sense, in the fact that the neutron interacts with the nucleus rather than the electron cloud, is that you have isotopic sensitivity and also a very non-uniform dependence in the scattering power going across the periodic table. So with X-rays, the scattering power goes as the number of the atomic number roughly to the fourth power. So as you increase the mass of the scattering atom, the scattering power goes up accordingly. For neutrons, on the other hand, the variation across the periodic table and even across isotopes is random because it's governed by the strong nuclear force. And that means that, for instance, hydrogen is highly visible to neutrons, where it's almost invisible to X-rays. And to demonstrate this, I mean, some of you who know me will know that I'm a big fan of coffee. Here is a video taken actually with neutrons of a little coffee pot boiling. So you'll see that the liquid here at the bottom is almost black, and that's because water scatters very strongly. So in X-rays, this would be almost invisible, but in neutrons, it's almost black. So you can see now how this coffee is making its way up into the chamber up here. Right, we won't watch that all the way to the end. I think they're boiling the coffee a bit too quickly anyway. Right, so as I mentioned just before, the neutron can not only exchange momentum with the sample, but also energy. So it can create or destroy excitations inside the sample. So again, inside a crystalline material, these excitations, at least structural ones, correspond to phonons. And neutrons are indeed one of the ultimate techniques to measure phonon dispersions in materials. So here you have the example of inelastic scattering from silicon, plotted along various directions in the Brillouin zone at various different temperatures. And you can see in great detail what the phonons are doing. And just to show you what these are actually like. So the top one here is an acoustic type phonon that you get near the Brillouin zone center, whereas the bottom one down here is an optical phonon that you get sort of at higher energies. So this is like a smooth distortion of the lattice, and this is a more energy demanding motion. So not only do neutrons interact with the nuclei of materials, but they also interact with the magnetic fields generated by unpaired electrons inside the materials, or in other words, magnetism. And this is one of the real unique features of the neutron, and it's thanks to the fact that it has a magnetic moment, as I mentioned earlier. So neutrons can scatter both from the nuclear and the magnetic parts of a sample. And indeed, just like you can do nuclear diffraction with neutrons, you can also do magnetic diffraction. So here is an example of a diffraction pattern taken on a so-called skyrmion lattice material. So this is a material where you have this interesting topological objects that form an ordered array like this. And these show up in the diffraction pattern as this six-fold pattern in the scattering map. And likewise, you can also look at magnetic excitations with neutrons. So the magnetic analog of phonons, if you will. So the example here on the bottom, these are both from the same material. It's copper sulfate. about a 5-gram single crystal. And on the bottom here, you have the spectrum measured along the chain direction. It's a one-dimensional material in a large magnetic field. So here you turn the material ferromagnetic, and you can watch the ferromagnetic spin waves dispersing in reciprocal space. At low field, on the other hand, this is a one-dimensional antiferromagnetic material, and the ground state of that material is not ordered at any temperature. And it's associated, this disorder, with unusual excitations called spin-ons, which can be imagined as domain walls propagating up and down the chain. And these spin-ons can be measured directly as these continua in the spectrum. So neutrons very directly access both the nuclear and the magnetic properties, both static and dynamic, of materials. And they do so across a very large time and spatial range. So here we have Q on the x-axis and energy transfer on the y-axis. And this range corresponds to roughly some fractions of a micrometer on this side, all the way up to some fractions of an angstrom on this side. And on the y-axis, going all the way from sort of nanosecond or sub-nanosecond dynamics up to many, many picoseconds. And these can all be accessed using different kinds of neutron instruments. And that's why we have such a variety of neutron instruments at ISIS. And reflecting the power of neutrons, they are applied to a vast range of fields, going all the way from biology and membranes, which I'll be talking about towards the end of the presentation, to chemistry, where they're used to look at systems like batteries, catalysts, polymers. Obviously, they have application in physics as well, and in engineering, and many fields beyond. So with that, I'll move on to polarized neutrons. So firstly, what is a polarized neutron beam? Well, the neutron has a spin of 1/2. And in an applied magnetic field, that spin can either point along or opposite to the magnetic field direction. And these states are called either up or plus, or, and down or minus. So that's for a single neutron. When you have a beam of neutrons in an applied magnetic field, we can define a polarization as the average of the expectation value of the neutron spin. And say the field is along the z direction, then that will actually be a vector pointing along z. And the magnitude of that vector, so the degree of polarization of the beam, will be the number of neutrons pointing up along z minus the number of neutrons pointing down over their sum. And why do we use polarized beams? Well, they give you extra information about the sample. So firstly, for nuclear scattering, the nuclear scattering length or scattering power consists of two components. There's a scalar part, which is spin independent. And then there is a spin dependent part as well, which arises from the interaction between the neutron spin and the spin of the nucleus. And since these nuclear spins are disordered at almost all temperatures, this leads to a disordered scattering contribution, which is called a spin-incoherent contribution. It can nonetheless contain information about single atom motions, and we'll exploit that in the final part of the talk. On the other hand, the first part, the spin-independent part, corresponds to the nuclear coherent scattering, as well as something called the isotopic coherent scattering, which comes about due to the random population of isotopes and therefore scattering powers that you have throughout your sample. So on the nuclear side, we have two contributions to the scattering: nuclear coherent and spin-incoherent. On the magnetic side, the interaction between the neutron and the magnetic field of the unpaired electrons explicitly involves the neutron spin as well. It's the dot product of the neutron spin and this B field generated by the unpaired electrons. And that crucially has a different dependence on the polarization to this spin-dependent interaction. So in other words, if we come in with a polarized beam, and we investigate both the scattering cross-section and the polarization of the scattered beam, we can, through these spin dependencies or lack thereof, get extra information about the spins in the sample. And this is implemented in many different ways. So some experiments just use a polarized incident beam and look at the scattered cross-section for different directions of the incident polarization. And this is a so-called half-polarized experiment. And it's often applied, for instance, in measuring reflectivity from thin film heterostructures. A slightly more sophisticated implementation, and the one we'll be discussing today, is longitudinal polarization analysis. So here, you're coming in with a polarization along a direction set by the magnetic field. The scattering then happens, and you analyze the polarization along the same field direction. And then you can repeat this for several different field directions to build up, sorry, a more complete picture of the components in the sample. I may remove the mask now, if that's all right. I think it's, oh, thank you. Right, so that's longitudinal polarization analysis, and it's used to, for instance, look at, in this example, the spin dynamics, probing different components of, in this case, the magnons, different spatial components, so transverse and longitudinal components. And the most sophisticated polarized neutron technique is spherical neutron polarimetry. So here one measures the full tensor of polarizations, so not just along the same direction for the incident and final polarization, but even rotations of the polarization. So you produce a 3x3 tensor called the polarization tensor, and this contains, in some cases, more information about particularly subtle problems in magnetic structure. So how does this actually look? So here's a cartoon sort of depiction of what a longitudinal polarization analysis instrument looks like. So you start with an unpolarized beam coming from your neutron source. It passes through a polarizer, which has an efficiency P, and you eliminate one of the spin states of the neutron and end up with a polarized beam. So here I've just chosen down for some reason. The beam then just passes through a device called a flipper, which, if it's off, does nothing to the beam. But if it's on, it flips the down to up, or the plus to minus, if you will. And this beam then hits the sample where it's scattered. And the scattering will change the polarization of the beam depending on the contents of the sample. So magnetic scattering will redistribute the polarization, and so will the spin-incoherent, while the coherent will leave it unchanged. And then after the sample, you analyze the polarization along the initial direction, and you record the number of neutrons. And appearing in this case, in the detector, is the so-called non-spin flip scattering. So the neutrons that are transmitted through the analyzer are the ones that weren't flipped in the scattering process. And this component contains all of the coherent scattering, 1/3 of the spin-incoherent scattering. And then for the magnetic scattering, it depends on whether you're measuring with a powder or a crystal. So in the case of a powder, it contains the squared dot product of the polarization and the scattering vector Q. In the case of the magnetic crystal, it's this more complex quantity, which is the component of the magnetization perpendicular to Q and parallel to the polarization. And likewise, if you now switch the flipper on, you measure all of those neutrons that are flipped by the sample. And this gives you access to this cross-section, which contains none of the coherent scattering, 2/3 of the spin-incoherent scattering, and then again, these more complex quantities for the magnetic scattering. So you can see already that if you have a non-magnetic sample, you eliminate all of these. then if you just measure the spin flip, that gives you direct access to the spin-incoherent component. And then subtracting 1/2 of that from the non-spin flip gives you a separation of the coherent component. So polarized neutrons are used to separate components of the cross-section in experiments, as well as components of the magnetization in magnetic samples. So that's a kind of cartoon picture, and this is how it actually looks. Well, I mean, obviously this is cartoon as well, but on an instrument. So you have a source over here. This is an instrument called COMPASS, by the way, at FRM2, which is a reactor source in Germany. So the neutron beam comes in from this direction. It's transported by sort of the neutron analog of optical fibers, neutron guides. And then over here, you have a polarizer that produces a single spin state. This is then reflected from a monochromator to choose a single wavelength as well. And then you have a pair of flippers on either side of the sample before you have an analyzer, which selects the final energy of the neutron, and a detector. So with this kind of setup, assuming that you have some fields that can rotate the polarization into any direction you like at the sample position, you can do this kind of experiment where you set up a coordinate system for the polarization where the x direction points along the scattering vector, y lies in the scattering plane, and z is vertical. And then you can measure the spin flip and non-spin flip cross sections for each of these 3 directions. And this, in the general case, will allow you not to only separate the spin-incoherent and the coherent scattering, but also all the magnetic scattering. So this gives you the coherent separate from the incoherent, separate from the magnetic, and it even gives you a bit more detail about the magnetic because you get the spatial components of magnetic scattering as well. Whereas in an unpolarized experiment, you would just be measuring the sum of all these contributions, and it would be a bit of a mess to analyze. Right. So that's the case for a single detector instrument. But often in neutron scattering, we want to measure with a big detector array. And that's because neutrons are actually quite hard to produce. And you want to detect as many of them as possible as a result to speed up the experiment, essentially. So there is an implementation of this longitudinal polarization analysis that exists for a wide-angle diffraction. It's only currently available on 2 instruments in the world, one in France and one in Germany. And it looks something like this. Again, you have a beam coming in, it's monochromated. There's a polarizer and a flipper, a set of coils that change the direction of the polarization at the sample position. And then you have in front of your detectors, which are these green points back here, a wide angle analyzer. This is just what it looks like. It's a set of mirrors that reflects only one spin state of the neutron. And now you have a coordinate system which is similar but not the same to the single detector instrument from before. Because this time with a wide angle detector, it's impossible to line up the x-axis with Q for every tube in the detector array simultaneously. And this makes the mathematical treatment of the data to do the separation a fair bit more complicated. But nonetheless, with a set of judicious assumptions, you can make the separation nonetheless, and you can get out your coherent scattering. So here, this is shown now along Q. So this is like a powder diffraction pattern. You get the coherent scattering, which contains the structural information separate from the incoherent scattering, the magnetic scattering. And again, you gain a lot of information over just measuring the total scattering. Right, so now we're going to go to spectroscopy and time of flight spectroscopy, which is the topic of this talk. So I will tempt fate at this point and try to click a link. And that looks like it works, although it's not shared. So let me take care of that. Right, here we are. So This is an animation of a time of flight instrument from the Institut Langevin, and regardless, I mean, this is from a continuous source, but regardless of whether your instrument is on a continuous or a pulse source, the instrument looks pretty similar. So yeah, you have a so-called neutron guide underneath this shielding, which transports the neutrons towards the sample. And inside this, there's a series of so-called choppers, which in the case of a continuous source, they pulse the beam. And you have several more that kind of shape the beam and narrow its wavelength range. Before you have finally a chopper right before the sample that takes only a very narrow energy range and allows it to the sample. And with the timing of these choppers, you know exactly when these pulses are arriving at your sample position. So what happens at the sample position is that the neutrons will scatter. Some of them will scatter elastically, and some of them will scatter inelastically. And since you know the time of arrival of the neutrons, and since you know also their wavelength and hence their speed, you can work out how much energy was transferred to or from the sample by measuring the time of flight from the sample to the detector. And this part doesn't work for some reason. But that's okay. Because that's the main point. So we'll go back to the presentation now. Right. Just a moment. Oh, there. Right, okay. Okay, so the instrument I showed you before, this diffractometer D7, it can be turned into a time of flight spectrometer by the addition of one of these choppers that pulses the beam. So you have then a monochrometer and a chopper that together create a pulsed monochromatic beam, and you can measure time of flight to the sample. And in this case, just because the experiments are so long, in practice, one only usually measures one polarization direction, so it's 1/3 of the measurement time. And that only allows one unambiguously to solve problems where you only have coherent and incoherent scattering. But there's nonetheless quite a lot you can do with that in non-magnetic samples. So here we have the example of an ionic liquid with two components. And the authors of this paper were able to separate the sort of collective part of the motions from the single particle part, which is contained in the spin-incoherent scattering using polarization analysis, and thereby get a better picture of the dynamics in this material. And this experiment, which was done back in 2013, really opened the doors for a lot of other possibilities. So for instance, this could be used to look at the diffusion of ions in batteries, where normally in unpolarized neutrons, the signal is too weak to observe. Polarized neutrons could help isolate that from the rest of the scattering. Or you can apply it to biological systems where you can use labeling with isotopes, so substituting hydrogen for deuterium to adjust the amount of incoherent and coherent scattering, and thereby address different parts of the molecule with a combination of that and the polarization. But actually implementing this on modern time-of-flight spectrometer is quite difficult. And that's because modern instruments tend to have enormous detector arrays. These are often tens of square meters large. And especially the height of these detector arrays is a problem, because you need a polarization analyzer that covers the whole solid angle of this detector array. And that, for various reasons, is very hard to build. So in addition to that, the low flux of these instruments the broad incident spectrum in terms of the wavelength range, and the complicated data analysis are barriers to the implementation of polarization analysis on time-of-flight spectrometers. Right, and that takes me to our attempt to do this on the LET spectrometer at ISIS. So LET is located on the newer target station, the target station 2, and it uses cold neutrons, so low energy neutrons, to look at excitations in both magnetic and non-magnetic materials. And LET looks something like this. So you have the neutron target over here. You have a neutron guide with several choppers along it going to the sample position, which is around about here. It's located about 25 meters from the source. A really unique feature of this instrument is the enormous detector array it has. So you can see here it covers about 180 degrees in the plane, and it covers about plus minus 30 degrees out of plane. And this is with a distance from sample to detector of about 3.5 meters. So this tank has a volume of about 40 cubic meters. It needs to be pumped down to quite high vacuum to do experiments. And at the back of it, you have about 40 square meters of neutron detectors. So this is really a huge, huge instrument. It operates in the energy range between about 1 and 25 millielectron volts. So that's cold to sort of thermal neutrons with a good resolution and flux, and a beam size of about 2 by 4 centimeters, which just emphasizes that for these experiments, you need big samples, typically. Right, so this is what it actually looks like. And here is a picture of what it looks like inside. So this here is my boss, Rob Bewley, who built this instrument, standing inside the detector tank. And you can see at the back here, the 4-meter high tubes, and the sample position is in here. And one of my other colleagues has called this a cathedral of neutron scattering, which if you go in there, it really feels that way. Right, so the science on LET, as I mentioned, is divided between magnetism, which actually constitutes most of the science program nowadays, and quasi-elastic scattering. So this is where you're looking at dynamics, often diffusion of ions or atoms inside materials. So the example here on the left shows the scattering pattern in momentum transfer and energy transfer from a one-dimensional chain in a magnetic field. And on the top here, we have the experimental data. And on the bottom, we have the simulation. This again emphasizes that neutrons are very, very good for looking at magnetism, and they provide a quantity that's very directly calculable by theory. In the quasi-elastic case, what one is analyzing is the broadening of this line along the vertical direction. So the horizontal direction here is the elastic line, where you have your diffraction pattern. Along the vertical direction, the energy transfer direction, you're looking at dynamics. And the width of this line corresponds to the inverse of the time scale of the dynamics. And you'll see in this case that the line broadens and then narrows again and then broadens again. And that spatial dependence tells you something about the geometry of motions in the material. So for instance, in the case of diffusion, what kind of distances the atoms are diffusing over. Right, another really good feature of the LET spectrometer is that its chopper system allows you to effectively measure with several incident energies at the same time. So on ISIS, you have a pulse of neutrons, which is very broad in energy. And using the chopper system, you can pick out individual energies for that and measure the spectra all together in one so-called frame, which is the time between two pulses. And you can combine this data to really span a huge range, in this case, in time. So this data is Fourier transformed from the energy to the time domain. And it's on this linear chain alkane, hexadecane. And yeah, you can go all the way from picoseconds to nearly a nanosecond in one shot. And typically on other neutron instruments, you would need to use several instruments to reach that kind of time range, at least using this technique. And when we were designing the polarized option on LET, we really wanted to make the most use of these unique features as we could. So we really wanted to be able to use, for instance, as much of the detector array as possible. And that really informed our design choices in adding polarization to this instrument. There was also a debate about whether to do uniaxial polarization analysis or full XYZ, which allows you to do a full separation of the cross-section in the general case. But for various reasons I won't go into now because I'm already running late, we ended up choosing the uniaxial variant, mainly because it plays to the strengths of the instrument, especially covering the whole detector. So the conceptual design looks something like this. So we have a polarizer a few meters ahead of the sample. It consists of two pairs of V-shaped mirrors that reflect one spin state of the neutron away and allow the other to transmit. That's followed by a flipper. And then around the sample position, we have an analyzer, which is a container full of hyperpolarized helium-3 gas, which analyzes the scattered neutron polarization. So how it looks in practice is this. I mean, for the people here who haven't seen one of these instruments before, this probably doesn't mean much, and I'd imagine that's quite many of you, so I won't really go into too much detail, but the polarizer is contained in this housing here. The flipper is a coil that you can hardly see inside there, and these are the performance characteristics of the devices which are within the design parameters, which are shown by the dashed lines here. I mentioned that we're using helium-3 as an analyzer. The way this works is that the absorption of helium-3 is a spin-dependent process, and you have a huge cross-section for that absorption if the spin state of the neutron is opposite to that of the helium-3, and virtually zero if the two are parallel. So if you can fill a sufficient pressure of gas into a container and put it in the beam and polarize that helium-3 gas, then you have a very good filter for polarized neutrons. And this is what that looks like in practice. So on the left, we have where we polarize the neutrons. This is a so-called MEOP filling station, which uses circularly polarized lasers to polarize the helium-3 gas. That gas is then transferred into these cells, which go into the experiment, onto the instrument. And you'll notice that these cells have the same shape as the LET detector. And all of this sits inside an insert that goes inside the detector tank of LET. Right, so now I'll just quickly talk through a few case studies. We installed this option on LET in about 2019. So now we've had a chance to do a couple of dozen, that's maybe exaggerating a bit, maybe 15 experiments with it. And the very first of those that involved external users, so ISIS is a user facility. We get most of our experiments come from academic users at universities, and that could include you if you have an idea that's suitable for neutron scattering. In any case, so this was an experiment looking at a liquid, so actually a very fundamental liquid, D2O, and the interest was looking at the coherent dynamics. So that's the collective part of the dynamics in the system. And this was done in collaboration with these people from the Universidad del País Vasco in Spain, as well as some people at ISIS. So the motivation for this was that previous unpolarized experiments on this system hadn't really given a clear answer as to what happens to the dynamics when you move to longer and longer length scales, to smaller and smaller scattering vector Q. So around the peak in the structure factor, which is shown by the black line here, things were fairly well understood, but going below that, it was found that the signal consisted of a mixture of incoherent and coherent scattering, even if you made the substitution of deuterium for hydrogen. So deuterium is often considered in neutron scattering a purely coherent scatterer, but it isn't actually. It does have a small incoherent cross-section. And it turns out that the two contributions to the cross-section become quite similar as you move down in Q. So basically, it was very hard to disentangle the single particle from the coherent dynamics in this system. And the authors of this paper, who were in fact the users who came and did the experiment on using polarized neutrons, had previously derived this curve for the relaxation time in the coherent and the incoherent channels. And they'd found that the coherent and incoherent were almost the same going down in Q, which was very strange because inelastic X-ray scattering, which probes the coherent part, suggested that the timescale should be a lot faster for the coherent than was observed in the neutron scattering. So this experiment was redone with polarized neutrons, and this is the result. So on the left here, we have plotted out in momentum transfer and energy transfer the incoherent part. And on the right side is the coherent part. So the coherent part is very strongly peaked at the structure factor peak, whereas the incoherent broadens out smoothly as you increase in Q. So this is the sort of the diffusive part, and this is the collective motions part. So this data was chopped up. So you take cuts along this direction, and you fit some Lorentzians, that's usually the relevant line shape, to this to get out the relevant timescales at the different Q. And this produces this plot. And you'll notice that this is extremely different from what you just saw. So here we have the blue points are the coherent, and these are measured at several different energies, as I mentioned before. The chopper system on LET allows you to do this in one shot. Whereas the incoherent is in red. So the incoherent has a sort of roughly Q squared dependence as you increase Q, which is completely consistent with sort of diffusive motions of the molecules through the liquid, whereas the coherent remains very fast in contrast to before as you decrease Q. So here we have the coherent, which saturates at roughly the value you expect from inelastic X-ray scattering, whereas before you had it shooting off to slower and slower times, which seemed very unphysical. So using polarization analysis, it was possible to solve this problem. And in fact, it was possible to supplement this with very detailed molecular dynamics calculations, which quantitatively reproduce these relaxation times. Right, so the second example is a very recent experiment. It was actually only a few weeks ago, so this is really not fully analyzed data, but activity has really been growing on this lately, and I was hoping to convey maybe a bit of the excitement that's around the technique at the moment by showing you this. So this was in collaboration with a group from the University of Manchester and the Institut Longitudinal in France, and it was looking at the diffusion of paracetamol in a bisurea gel solvent mixture. And this is actually a very relevant problem because pharmaceutical companies are investigating these for drug delivery. So these gels, they are composed of molecules that sort of self-organize into anisotropic rods. And these rods make a sort of spaghetti that the solvent and the drug molecule diffuse through. And interestingly, these rods, they actually speed up the diffusion, hence why these are being considered for use in drug delivery. So here are the spectra. Again, these always look very similar, these S of Q and omega, so-called. Regardless what you're measuring. So in the incoherent, you always have something that drops off and broadens out. And then in the coherent, you always have something that's peaked at some momentum transfer. But again, if you analyze this, and before I go to that, actually, I should mention that this was paracetamol in a 7:3 ratio of D2O to ethanol. And both of these were fully deuterated, whereas the paracetamol had protons on it. So this signal should be dominantly from paracetamol, while this should be dominantly from the solvent. And the gel doesn't really contribute at all because it's only about 1 weight percent of the total sample. So here's an example of a couple of cuts through that line and how you fit them. So it's usually a combination of different Lorentzians, and then you fit the width of those Lorentzians, and from that you extract the time scale of the dynamics. So one can make a plot of the time scale of the paracetamol dynamics from this versus Q squared. And you can see that it doesn't quite follow Q squared. It's not a straight line, but it can be fit by a jump diffusion model, which involves it hopping some distance inside the channels formed by these self-organized gel rods. Right. So I think given the time, I'll skip over this example and I'll go straight to the biological one. So here, the interest was in tail group correlations in lipid bilayer systems. And this was done with a team from the National Institute for Standards and Technology in the US. So the interest in this is motivated by trying to understand the cell wall and how it works in living cells. So how it moves, how atoms, especially ions, move through it, and so on. Sorry, this is really not my field. So, but in any case, this is a very complicated system to deal with in a living cell. And so the tendency is to try to come up with suitable models for it. And this is apparently one such very popular one. It's called the MPC. And it consists of a head group, which has this sort of phosphate and ammonium on it, and a tail group, which is a long carbon chain. So this part is a hydrophilic part, and this is a hydrophobic part. And that makes, when these things are in solution, the molecules self-organize into these bilayers, where the hydrophilic part faces the solution, which is usually a polar solution like water, whereas the hydrophilic part points inwards. And in this case, the team, they deuterated the tail groups. So they were interested in the coherent dynamics of these. So basically how these wave back and forth inside this structure. So you can imagine them waving like horizontally. And they kept the head group protonated. And before looking at the dynamics, here is what happens on the elastic line. So this is effectively the diffraction in this system. And you see that at low temperature, you get something quite sharp, 2 peaks actually, one at quite small q and one at about 1.5, which corresponds to the self-organization of these molecules into the lipid bilayers. And here we have that separate from the incoherent signal, which would otherwise produce a very large background, and that's shown in blue. As you heat up, this basically all broadens out, and that's these layers kind of falling apart, losing correlations, losing coherence between each other. And the interest was what happens to the dynamics as this process occurs. And to look at this, the most sensitive region is the one near the peak in the structure factor, because that's the part that captures the correlations between these tail groups. And this is what the spectra look like. Again, you know, fitting these is a rather technical matter, but what the authors found is that in the coherent, that's the filled red points, and the empty blue points down here, there are 2 dynamic processes, each represented by a Lorentzian. And this is, again, very recent data. So they have a good idea now what one of those processes might be, but they need more simulations to work out what the second one is. Right, this one I'll also skip over. And then I'll finish maybe with this example. As I mentioned earlier on, one of the possibilities that's opened up by polarized neutron scattering is actually looking at the diffusion of, for example, lithium or sodium in battery materials. This is a hugely technologically relevant problem, but one that's been really hard to address because both lithium and sodium scatter very weakly. And so we tried doing this with polarized neutrons. This is a team from Stavanger in Norway and the Royal Institute of Technology in Sweden, as well as Robin Perry, who's at ISIS. And the problem specifically was looking at diffusion in a so-called LLZO electrolyte. So this is lithium lanthanum zirconium oxide material. It's a garnet. It has a cubic structure. And on the left here are the proposed channels that the lithium might diffuse through in this structure. And the mechanism of the diffusion is thought actually to be quite complicated. So it's thought to involve some kind of concerted hopping of lithium between sites, because there's really a lot of lithium in the structure. It can't move sort of freely, ballistically. It has to be a collective motion of the lithium. And we tried to investigate that with polarized neutron scattering. So looking at the incoherent part for the self-diffusion. So trying to get at the timescales for the diffusion. And then the coherent part to look at some of the mechanistic details involving this collective hopping. Now, this is an extremely difficult experiment, and unfortunately, it was cut rather short. This was done right before I came here to Sao Paulo. So this is a very preliminary analysis, but we do see some broadening. It's very, very weak, but we do see a broadening that corresponds to the self-diffusion part. And the coherent part hasn't been fully analyzed yet. Right. And this is just a technical part here. Actually, do I have time for this? What is the time now? 5 more minutes. Okay, I'll just skip over this because it's a bit long and technical to explain. But essentially, it's a method where you use the variation of the magnetic signal along the vertical axis of the detector to do what you'd normally do with an XYZ type polarization analysis experiment and separate all the cross sections. So it involves fitting lines along rings in this detector. This is a method that's only valid for powder samples. And from these fits, one can actually get a very, very good separation of the full cross section into magnetic, that's the yellow points, spin-incoherent, that's the red ones, and coherent, that's the blue ones. Right, so I've hopefully showed to you that polarized time-of-flight spectroscopy has shown its potential for quasi-elastic neutron spectroscopy, especially on a range of systems in soft matter and biology, as well as some hard condensed matter systems. Polarization analysis is really crucial when you're looking for weak scattering signals, or if you're looking specifically for coherent scattering, so collective kind of dynamic processes. The technology is now mature to attempt more complex systems. You'll notice that from the D2O example going on, we were doing more and more complicated things. And we're keen to try pushing the technique even further. But user communities for this need to be built. And this is where I welcome you all, if you have an idea, to please come and talk to me after the presentation is finished, or write me an email. So single crystal magnetism, which is kind of the core case for doing polarization analysis, is quite difficult on the current instruments just because of flux. These experiments just take too long. Magnetic signals are too weak, and the beam time is too valuable to spend on that kind of experiment in most cases. And the final thing is we also need higher resolution in time. We'd like to be able to resolve slower processes, and we've actually come out now with a concept instrument that hopes to address that hopes to push towards the nanosecond regime. And with that, I'd like to thank all the collaborators who worked with me on the LET project, building this polarized option, especially Mark Davenport, the technician who put a lot of the equipment together, and Ross Stewart, as well as a group of students who helped do the simulations and write the software and so on to do the data analysis. And here especially Gino Casella. And I'd also like to thank FEPESPI very, very much for the opportunity to come here. And also again to Professor Julio and Professor Valentina for hosting me for these fantastic 3 weeks that I've had here so far. And with that, thank you all very much for your attention, and apologies for overrunning by several minutes at the very least. Thank you very much.
Okay, so thank you very much, Dr. Nilsen, for nice talk and very instructive to see also the perspective of neutron scattering, many type of case study in condensed matter physics and beyond. So now we are open for questions. Is just someone have a question? Just ask me to bring the microphone there.
Towards the end, you mentioned this, maybe you can go back a few slides.
Sure.
This difficulty that flux, single crystal, the difficulty for single crystal towards the very end, you know.
Oh, so
here, single
yeah.
crystal magnetism, because, you know, it's a question, you know, of flux. Is there an alternative currently that you could use in the market to do these kinds of experiments, or is there anything in the works for something with higher intensity?
So to do it on this kind of instrument, you basically need a better source, and there is one on the way in Sweden, the European spallation source, which will probably by around an order of magnitude exceed anything that's available today. On the other hand, that kind of experiment is very possible to do if you know what you're looking for on the first kind of instrument that I showed, this one with a single detector and a monochromator and an analyzer to select the incident and the final energies. So on a triple axis spectrometer, you can do quite a lot of this science. But the advantage of these time of flight machines is that they give you an overview over huge ranges in time and space at the same time. You have to map out each point by moving the instrument physically. You only have one detector, so it can be quite time consuming, and as I say, you need to know what you're looking for.
Thank you.
So, Oscar?
Okay, thank you, nice colloquium. And one thing, I'm curious, what's the efficiency from starting with protons and end up in the experiment? How many start and how many end up per spill into the experiment?
So the neutrons that are actually generated in the source and make it to the sample.
Yeah.
Oh, it's very few.
Very few.
So you have usually from the source 10 to the 13 or so 10 to the 14, some very powerful sources 10 to the 15 per second. And actually getting to the sample on an instrument like LET, you have maybe 10 to the 5. So it's a huge reduction. On a diffractometer, where you don't need to chop up the beam like you do on a time of flight machine, you can get up to sort of 10 to the 8 or 10 to the 9. Yeah.
One curiosity: you have the detectors and the polarization analyzers after the collision. How fast can you reset those?
Right. So basically, the polarizer is completely static, and that's why we need a flipper. So the polarizer is in most cases either mirrors or a set of crystals that reflect a single spin state. And there, I mean, you could sort of physically rotate the whole instrument around, but often they're just left static. And then instead you use flippers to change the spin state, both before and after scattering. In the case of our analyzer, helium-3, you can actually change the orientation of it on the instrument, but it requires applying a radio frequency pulse to it over the whole volume of it with quite a lot of power. And for cells this big, it's just not feasible. So for instruments with smaller detectors that have smaller helium-3 cells, you can do that. Another point is that the helium-3 polarization decays in time. So once you prepare it in the filling station and fill it in, it has a finite lifetime. And here, this is the time it takes to decay to a polarization of 1/e. So that's 50 hours. It's an exponential decay. So in practice, that means that you need to change this every 24 hours. Fortunately, we can recycle the helium-3, so none of that is lost. But it takes a little bit of time to take it out. We have 2 of these cells, fill the other cell and put that back in. Yeah.
One last curiosity. I saw that the results that you showed are around room temperature.
Mostly, yeah.
Are you able to go down with the temperature?
So with this setup, we have a specially built, rebuilt cryostat for this. So with this, we can go from about 1.8 to 550 Kelvin. We're working now on a furnace to go up to hopefully near 1,000 Kelvin.
So Renato?
Oh, thank you very much for your nice talk. And I would like to know a little bit more regarding thermodynamic parameters like temperature and varying applied magnetic field. Are you guys able to make measurements under applied magnetic field?
Unfortunately not. So the helium-3 is very, very sensitive to field gradients. So it can only tolerate transverse field gradients of up to 10 to the -4 relative per centimeter. So if you wanted to measure a magnetic field, it would have to be an extremely well-shielded magnet, or you'd have to put the helium-3 cell in a superconducting box or something like that. So unfortunately, with this setup, it's not really possible. But with other setups where you use mirrors instead, it is generally speaking possible. Yeah.
Well, another question.
So for those of us interested in lattice dynamics, how exactly is the phonon density of states calculated from these experiments?
Well, I mean, for that kind of measurement, you usually measure on a powder because you're interested in density of states. You don't want all the detail that you get with a single crystal. So, I mean, I don't have an example in here, but I mean, you basically, you just take your Q energy map. I'll just go back to the phonon figure now. So if you imagine now that we're not resolving this in the Brillouin zone, we're just measuring the powder average, but we have a sort of Q energy map. All you do is apply a weighting factor and integrate over all Q, and that gives you the phonon density of states. And that weighting factor is to account for the fact that the window that you actually measure doesn't extend infinitely in Q, and in fact it has a curvature in this Q and energy space. But this is not something I've done. But if you look up some phonon density of states papers in the neutron scattering literature, it's a pretty routine conversion to make on the data. Yeah.
I see. Thank you.
Professor Nilsen, yet about nuclear and elastic scattering to obtain information about neutrons, I would like to know what is the resolution in energy and momentum when you obtain these dispersion curves for the neutrons?
This is a very good question and a very difficult one to answer, unfortunately. So it depends on the type of instrument you're measuring with and the geometry of the instrument as well. So it's usually, I mean, for instruments like this, this is from a time of flight instrument. It's a non-analytic function, and it's often something that that you have to simulate, or there are a few analytic approximations you can use as well. But it's basically an ellipsoid in all directions in reciprocal space and energy, and you integrate kind of over the volume of that ellipsoid, and in the case of a time-of-flight instrument, along the energy dimension especially, that the extent of that ellipsoid will depend on how fast you're spinning the choppers, so how well defined the beam wavelength is. It will depend also on the divergence of the beam. So as I said, we use something like optical fibers to transport the neutrons down to the sample. But of course, that involves reflections, and these reflections will generate some divergence that also gets convolved in with the resolution. So typical energy resolutions are from like 1 to 5% of the incident energy that you use, depending on the chopper settings that you use. And then the resolution in Q depends mainly on divergence, but also things like sample size. Energy resolution also depends on the length of the instrument, especially in the case of these instruments, on the distance between the sample and the detector. So it's quite a complicated quantity to calculate.
But yet about resolution, there's some limitation on very low energy modes or very flat energy modes.
So basically, if you're interested in low energy modes, what you'd usually do is reduce the incident energy, because the energy resolution goes as that. So of course, if you want high resolution at high energy, well, actually on a direct geometry time of flight, the resolution actually gets better as you go up in energy transfer. So you may have a chance, but you have to think, always doing these experiments very carefully about what settings you want to get the resolution and other characteristics that you want, the coverage especially. So the coverage in Q and energy of the features that you want to see. Yeah.
Thank you very much.
Okay, further questions? Okay, so now I'm allowed to make some questions. Maybe I have a couple of questions.
Mm-hmm.
The first one is, I was actually curious about the way how it's generating these polarized neutrons. And in particular is the time or the period of time flight that apparently is somehow done for investigating this dynamics, right, process. And I was thinking about muons in general that you also, let's say, covers a process of dynamics in spin relaxation or spin fluctuations.
Yes.
And then my question is whether a polarized neutron also could somehow improve the time relaxation process or dynamics or spin dynamics in like muons cannot do.
Well, so there is actually a technique that's more like muons. So with muons, you implant the muon in the sample and it processes in the internal fields inside the sample. So it's a little bit like NMR in that sense. The neutron analog of the technique is called neutron spin echo. And there you use a polarized neutron beam. Well, it's a little challenging to explain, but you essentially have two arms of the instrument where you're processing in one direction for one arm and the opposite direction of the other arm. So with no sample in place, you're supposed to just recover the polarization that you had at the start. But if the sample scatters inelastically, so if neutrons speed up or slow down, they will do a greater or smaller number of precessions in the second arm of the instrument, and you see a depolarization. And this depolarization actually is extremely sensitive to the dynamics. So you can, using that, you can get all the way up to sort of, in the extreme cases, microsecond dynamics. So then it kind of overlaps with muons. But for most sort of conventional neutron techniques, you're limited to about 1 nanosecond, roughly time resolution, which is kind of the upper end as far as I remember. I'm not a muon expert. It's kind of the upper end for muons. Yeah.
Okay, thanks. And the second question is just also another curiosity that caught my attention at the beginning of your presentation, the way how it distributed, for instance, the neutron, right, accelerator close to some companies there, technological companies, where then I don't know from which percentage of this granted beam time of neutrons actually are accessed to these industrial companies.
So it's a fairly small proportion. I think it's probably in the region of 5% or so of the total beam time, 5 to 10%. I mean, we have several ways that industrial users can actually engage with us. So they can either engage in a sort of collaboration with us, in which case they agree to publish the results in the normal scientific way, in which case the access is free. And I don't know if that is actually counted under the industrial access statistic. They can also, if they want to keep their results secret, they can pay for beam time as well. But as I say, this is quite a small fraction. There is actually one instrument on here, which is specifically designed for industrial users, which is called CHIP-IR. So it essentially simulates the spectrum of cosmic radiation. And it's used by companies that design things like electronics for spacecraft and so on, to simulate the faults that this radiation causes in the electronics. And I think there's a group working very actively on that here in Sao Paulo. Paulo Rech, I think, is the name of the professor. I think he's in the electrical engineering department.
All right. Further questions? Okay. If not, let's thank again the speaker.